Hello and welcome to a new video. This is for Precalculus using the Math UC curriculum. We are on lesson 16, which introduces the idea of polar coordinates. So here's where we're at. At this point, you've done all your graphing on the Cartesian coordinate plane, probably, unless you've just randomly done this before, which could happen, I guess. But what we're familiar with in Algebra 1 and Algebra 2, and even in geometry, is called the Cartesian coordinate plane. It was kind of originated from this guy named Descartes, who lived a long time ago, but that's where we get the name Cartesian, is from Descartes. And it's also known as the rectangular coordinate plane because the emphasis in this way of graphing is the idea basically of having a grid. And so there's another way that we can actually graph things. There's probably more than actually these two ways, I'm sure. But another way that gets its use some in higher level mathematics in particular is called the polar coordinate plane. And the polar coordinate plane says instead of going with like a left or right and an up and down sort of system, what if we use an angle and a radius? So you can see that I've got this this graph that looks kind of like a sonar from a submarine or something like that. And so this is what you could use for graph paper for polar graphing, because what we're doing is we're saying I'm going to go around to a certain angle and then I'm going to count out a certain amount, and that's where I'm going to put my point. So for instance, if I have 5, 45 here, the 45 is talking about the angle. So we would come over here and we would attempt to make a 45-degree angle. Typically, anytime I've done this, it's just been that we've kind of approximated this. You could pull out a protractor to get a more exact 45-degree angle, but so somewhere along this line is the point 5, 45 degrees. Since it says 5, we're going to count out 5 from the origin along this line. 1, 2, 3, 4, 5. So kind of the fifth circle. You also might be thinking of electrons and how that all works. But this would be the polar coordinate 5, 45. So there's a couple of intricacies here that we'll look at and discuss. One is that we can have positive values for these two coordinates, like 5, 45, or we could also have negative values. So a negative angle is going to be the same thing as it has been for us. So this is going to be 0 degrees or 0 radians. So positive 45 went counterclockwise. Negative 45, for instance, would go clockwise. So would have been down here instead. This would be where negative 45 is. What's a little bit weird, I'm going to admit to you that I find this weird, and you probably will too, is the way we deal with having a negative radius. So if this said negative 5 instead of positive 5, what we do is we extend our line for 45 to the other side of the origin, this way, and then count 5 that direction and say that that's negative 5. So 1, 2, 3, 4, 5. This would be negative 5, 45. So it's kind of weird because we're still talking about the same angle, which is in the first quadrant, but negative makes us go across the origin to the other side. It's kind of cool, kind of weird. That's how we deal with negative. So we're going to do kind of 4 types of problems here. We're going to do graphing based on being in degrees to start. We're going to do graphing if we have radians to start. And with both of those, we're also going to talk about how we can name these points different names. Because just like how 45 degrees can be named other angles, we can just name these points differently and be talking about the same angle. And then we'll look at converting between the two types of coordinates. Because for one thing, we're kind of stuck in the rectangular coordinate plane, that's kind of the way our minds think. So there may be times where we want to switch back and forth between them. Because there are certain graphs that are either much easier to graph in polar coordinates and as a polar equation, or it could just be that that's the only way we have to graph them, maybe. So that's going to be next week, though, that we look at actual graphs using polar equations. So that's exciting. There's some really cool graphs, so you're going to want to make sure to come back for that. So here's kind of a summary of our information. So these are called polar coordinates. The first coordinate is talking about a radius out from the origin, And theta is talking about an angle starting from normal position, what we're used to, which is good. They didn't switch up where we start counting from. That would have been weird. These next things are how we actually convert between the two. And it all comes down to thinking about having a right triangle. So for instance, if we have this point right here, and we wanted to think about what that is, pretend that's a right triangle. If we wanted to think about what this is, and we've been given r and theta, we've got a right triangle and can use right triangle trigonometry to figure out what the sides of this would be. This would be our x and this would be our y. So we use cosine to find our x because it's talking about the adjacent side. We use sine to get y because that's our opposite side. So hopefully those two formulas make sense, that x equals the radius times cosine theta, y equals the radius times sine theta. If we're going the other direction and we're given a rectangular coordinate and we want to change that into polar coordinates, again, we're just using what we know about right triangles. So x squared plus y squared equals r squared should look familiar. That is the Pythagorean theorem, just with different letters than what we normally have. And then the theta has to do with, some of these we might be able to figure out because they're special right triangles, but for others, we'll have to think, okay, here's the angle. I'm going to use the opposite side and the adjacent side, which means I'm going to use tangent. I'm going to inverse tangent so that I can find the angle. And we're going to work through all of that here in a little bit. One of the things to note is that we will be doing some problems in degrees and some problems in radians. So for one thing, if you end up using your calculator for some of this, make sure you're in the right mode. Typically, if you're in the wrong mode, most of the time you'll get an answer that you're like, I don't quite think that's right. So just keep that in mind. And then the other thing is that we just started using radians last lesson. And so they may not be super familiar to you. I plan to have another video out around the same time that helps you fill out a unit circle with radian values, because basically I think what would be most helpful in this lesson is to have a unit circle or some reference next to you so that you're not just getting like totally lost by trying to figure out where 2 pi over 3 is or something like that. You can work on memorizing them later if that's something you need to do because you're planning to take calculus next year. But for now, at least, we just need kind of a reference. So either print off a unit circle from the internet or take a look and see if you can find that video that I am going to make somewhere around the same time that I'm making this one. Not at the exact same time because that's impossible. But anyway, let's look at some examples. Example 1, plot the polar coordinates and describe the answer 3 more ways using degrees. So they're giving it to us in degrees, and we're going to have to come up with 3 other ways to name it. So the first thing we do on each of these is we go to the angle. So negative 30 degrees is going to go clockwise 30 degrees. And again, this is approximate. So I can just kind of make a line that looks like it's negative 30 degrees. And then I follow that line out for the radius 3 spots. So I'm going to count out 3 circles. 1, 2, 3. If you do not have this kind of graph paper handy, for one thing, you could probably find it on the internet pretty easily by Googling polar coordinate graphs, blank polar coordinate graphs. Or if you just don't want to be bothered to have the circles, you'll see people just make tick marks along the line to show that that's 3 out, and that's fine too. So that's how we kind of deal with that situation. So we've got this plotted, and since we're going to be putting 2 things in the same graph, I'm going to label this 3 comma negative 30 degrees, and then, or I could have labeled it A. But now we need to come up with 3 other ways to name this using degrees. And so this goes back to the idea that we went over like way back when I think at the beginning of the school year, that angles can be named different things. So we've got negative 30. What's the positive version of negative 30? If you have a unit circle with degrees on it, you can look for where this line is, and you can see that the positive angle for it is 330. The other way to come up with that is to say, well, what's 360, which is a full circle, minus 30? That gives us 330. So we can put 330 here, and we can still put the same 3, because if we went around to 330, we'd still need to go out 3 spaces. What are other ways we can do this? We can always add 360 to get a coterminal angle is what they're called. So that would suggest that you went all the way around the circle, that's 360, and then you went the 330 to get to 330. So that would be 360 plus 330, which is 690. That's an option, and then we'd still have the 3. The other kind of common option that we would have here is to say, how would I make the 3 negative? What angle would I have to be talking about to make that happen? So for that, we need to actually come over to this side across the origin and need to figure out what this angle is, where this right here is 30 degrees. So, and this is 180. So what angle is 30 degrees shy of 180? That'd be 150. So if we went around to 150, we'd have to then go backwards to get to where our point is. So that's why this works, that we'd have -3, 150. So that's just 3 of the ways that we could name them. There's actually infinitely many ways that you could name them because of the fact that you can keep adding or subtracting 360 to these angles basically indefinitely until you had as many as you wanted to. So that is example 1A. Let's look at 1B. So -2, 60. We're going to start by drawing 60, which is something like this. And then since it's negative, we need to go the opposite direction too. So I'm going to continue my line this way. It's supposed to be a straight line across the origin so that it's not like a V or anything. It should be just a straight line. And the importance of that, by the way, is that then these angles are actually 180 degrees apart if they're on a straight line, just by the way. So we have 60, we're going backwards 2, so that would be this point right here. And then we label it -2, 60, and let's name it some other names. So one thing we could do is we could talk about what angle would we need so that this would be +2 instead of -2. So what is the angle to get around to here? Well, I just mentioned that this is 180 degrees more than 60 because they're on a straight line. So we do 180 plus 60 and get 240. We also could just use -2 and add 360 to 60, or subtract 360 from 60 and get angles by either going around an extra time or going around backwards. So 360 plus 60 is 420, and 60 minus 360 would be -300. So to get around to this angle, we'd have to do a -300 to get all the way around there. Or I could have done more angles that had the +2 for the radius if I'd wanted to. The possibilities are endless. That you may have come up with some that I didn't. And keep that in mind as you're looking at solutions. I actually haven't looked at the solutions yet. It's on my list of things to do. But your solutions might have different answers than you do. And so knowing how to check to see if your solutions are right, even if they're not actually the solutions, is, an important skill to develop. So good luck with that. All right, let's do the same thing, but with radians. So this is where having a unit circle with radians filled out is going to be probably make a huge difference on the time it takes and the frustration it takes for you to do this, because we're still, like I said, we're pretty new to radians. And so I don't think that most of us would just naturally know where pi/4 or 11pi/6 are. So let's dive in. One of the ways you can do this is you can actually just convert them to degrees. But if you have a unit circle that tells you where these are, that would probably be even better. So pi/4 is a fourth of a pi. Pi is the same as 180. So if we're going a fourth of the way to pi, that's going to be it is a 45-degree angle. Here's pi/4. And then we're going to go along this 5. 1, 2, 3, 4, 5. So here is 5, pi/4. Now, naming these other names is going to be tricky because we are in radians. So with degrees, we added 360. So we need to think, well, what is 360 in radians? 360 in radians would be 2 pi. A whole circle is 2 pi. So let's take pi over 4 and add 2 pi. Now, that might seem a little bit weird to you, but we have a fraction and a non-fraction, so we need to make them have common denominators. In order for this to turn into a 4, we need to multiply this by 4 as well, so that we get 9 pi over 4. That would be if we went all the way around the circle and then back to pi over 4. So 5 comma 9 pi over 4. Kind of the other standard thing that I would do is say, well, what's the negative angle to get to pi over 4? Because if you have your unit circle, if whatever angle you're looking at, the negative angle that goes with that is the one that's symmetrically below the x-axis. So in this case, that would be 7 pi over 4. So we could do 5 comma negative 7 pi over 4. Because that's, like I said, the positive angle, 7 pi over 4, is down in the 4th quadrant. But if you're trying to think of the negative, the negative direction, pi over 4 plus 7 pi over 4 is 2 pi. So together, that positive and negative angle make a whole circle. I don't know if I'm doing a good job of explaining this. I'm so sorry. We need one more way. So we could just add 2 pi to one of these again, add or subtract 2 pi to one of these. Or we could say, well, what if we want the negative angle? What is this angle over here in radians? Not negative angle, negative radius. So if I wanted to say negative 5, I'd have to think of this angle on this side, which if I look at my unit circle, I can see what that is. Or this would be like adding pi, which is 180 to pi over 4. So we'd get 5 pi over 4 for our answer to that one. So that's just a few possibilities that we could pick. Let's look at B. 11 pi over 6 is in the 4th quadrant. It's down close to 2 pi. And then we want to go negative. I didn't actually quite go through the origin there. Whoops. So that'd be this way. We want to go negative 2, so 1, 2. That's negative 2 comma 11 pi over 6. And then we would name this other name. So we could say, well, what's the actual angle to get around here? And use positive 2. So let's see, that's a pi over 6 short of pi, so that'd be 5 pi over 6. We could use the negative angle to get here, because that's just pi over 6. So that would still be negative 2, because we have to go backwards along that line. But it'd be negative 2, negative pi over 6. And then for either one of these, or for 11 pi over 6, we could just add 2 pi. And get the same thing. So if I wanted to do that, I don't know, I feel like doing that with 5 pi over 6. If I add 2 pi to 5 pi over 6, I have to get a 6 on bottom, so that's 12 on top. That'd be 17 pi over 6. And it'd be 2 because we went all the way around this circle and then to 5 pi over 6, and it's along that line, the positive direction, so positive 2. Example 3 and example 4 say to change the polar coordinates to rectangular coordinates and graph. So it doesn't actually, I don't have on here that we need to use exact values. If we needed exact values, that would imply that we had special right triangles that we could use. If we want to just get the decimals, then we need to make sure that we're in the right mode on our calculator, because these angles are in radians. So I think it's actually helpful to graph it to start off, just so you have an idea of where it is. 2 pi over 3 is in the 2nd quadrant here-ish. Oh, but we got to go down here. 1, 2, 3. So that's how I would make those tick marks. So here is negative 3 comma 2 pi over 3. Now we have formulas on that slide earlier to help us with this, because our hypotenuse, it's saying, is 3. We're trying to, let's see, this was 2 pi over 3, so I guess we don't actually know what this angle is. We have to figure that out. That should be pi over 3 in radians, or 60 degrees in degrees, which you can figure out by kind of comparing where this is on the unit circle with like how far apart the little sections are on your unit circle. If we're just like, I just want to plug this in, then here's what we could do. We could do x equals -3 cosine 2 pi over 3 and y equals -3 sine 2 pi over 3. That'll work. We could work this out using special right triangles and thinking about it, and that would be fine too. But let's try this in the calculator. I'm going to do Desmos, and Desmos defaults to radian mode, so that's good in this case. And to do pi, you can type pi and it switches it to pi. Oh, I don't want to do that. The answer here is 1.5. And if we'd used special right triangles, we would have gotten 1.5 or 3/2, so that checks out. If we do this with sine, well, I can actually just edit this and make it be sine instead. Now this is not as pleasant because this is actually like 3 square roots of 3 over 2 or something like that. So -2.598. I did not mean to make it look like a fraction. I was thinking fraction, but then I was like, that's a decimal. -2.598. So there we go. If the solutions had it as a radical situation, if you type it in and compare the decimals, that would tell you if you're correct or not. I personally at this point am kind of fine. I'm fine with the decimals because I feel like we're doing a lot of other things that are difficult. And so adding to that, you having to do the exact value seemed a bit much. But definitely if you have a different teacher, then whatever they say is what you should do. Let's look at B. One of the reasons I like to graph it to start off with is because occasionally you end up with a really easy situation. 4 comma -pi over 2. -pi over 2 is straight down because you go -90 degrees. And then 4 would just be 4 along this line. And we actually can figure out this coordinate without doing any work because we literally went down 4. So that's 0 comma -4. Now, if you do work it out as x equals r cosine theta and x equals r sine theta, you should get 0 and -4. Oh, I guess I should have written this as a point. That would be the whole point of this, is to write it as a point. So there we go. There's our 2 points written as rectangular coordinates. Now let's go the other way. So this says change the rectangular coordinates to polar coordinates in graph. It doesn't say whether to use degrees or radians, so I'm going to use degrees because I think that is a little bit easier conceptually, but you could use either. So -3 comma 4, again, I'm just going to go ahead and graph that. 1, 2, 3, -3 positive 4. I feel like I said negative, but I don't know. That's here. We could draw a triangle, and that's actually a good idea on this one because it helps us visualize what we're finding, right? We're finding the radius of this, so that's the hypotenuse. You might already know what it is because this is not a special right triangle, but it is special because this is a 3, 4, 5 triangle. So R should end up equaling 5. So that's our hypotenuse. And then to find the angle that gets around to here, we actually need to find this angle. So this is one of those like tricky conceptual things. I need to inverse tangent to find this. And if you do inverse tangent of 4 over -3, I'm going to switch to degree mode because I think having it in radians actually just makes it that much harder. If I do inverse tangent of 4 divided by -3 versus me doing inverse tangent of and ignoring the negative. In both cases, I get 53, but when I have the negative in, it gives me -53. When I don't put the negative in, it gives me positive 53. But what we need to realize is what this is actually telling us anyway. The angle that's 53 degrees is this angle inside right here. That's what we found, that's 53. So in order to actually figure out what the angle is to get around to that, we actually need to do 180 minus 53.13. Just double checking. So there is kind of a connection that we did get a negative when we put in the negative. So I believe if we'd done, if we were thinking about this one down here, we would, we'd want to do 180 plus 53, and our answer should have been positive. So there is a connection there that we can make. But it is a little bit weird to get used to, especially because we haven't done a ton of problems like that. If we do 180 minus 53.13, we get 126.87, I think. And so our answer is 5,126.87. Actually, that's just one answer because we already know that there are infinitely many answers to this. So keep that in mind. Let's look at B. So the fact there's square roots suggests to me that this is a special right triangle. So that's certainly something you could do, is use special right triangles. Now, I don't know what 4 square root of 2 is off the top of my head. It's probably 6 something. I don't know. So I'm just going to go out and down. And what I am going to realize is that, this seems like it's going to be a 45, 45, 90. Because that's the only situation where our sides end up being the same. So this actually would be, that negative's in a weird spot. This would be a situation where it's actually pretty easy to be like, well, I know what that angle is. That's 45. Because this is a 45, 45, 90. And so either we could do the positive angle to get around, which is 315, or we could use the negative angle to get there, which is negative 45. Your choice. And then our radius, we can use the Pythagorean theorem for, or we could try to reason it out using special right triangles. That's not what I wanted to do. If you do the Pythagorean theorem, when you square 4 square roots of 2, it squares the 4, so you get 16, and then it squares square root of 2, so you get 2. So this would be 32 plus 32, which is 64. And then we square root and get 8. So the radius of this is 8. So 8 comma negative 45 degrees. Thanks so much for watching. I hope you enjoyed this. It's kind of a weird thing to think about, that we could graph things in a completely different way than what we're used to. And like I said, hopefully you'll like next week seeing what we can do with this that may have seemed not possible to do before, depending on how much you've played around on your calculator anyway. So again, thanks for watching. Feel free to give me a like, and please subscribe if you haven't already, and I'll see you in the next video. Bye.